Alright, so in this video we're going to be working with a Fluke 566 IR thermometer used for non-contact temperature measurement. So what I wanted to demonstrate first here, we've got an IR calibrator right here. It's set for 100 degrees Celsius and right now it's about 93.5. So over here is our aperture surface there, simulating a black body, and that's why it's black in color, and it's kind of a dull black. It's not shiny. Reflective surfaces tend to make it challenging to measure the temperature of them with radiation measurement. So what I'm going to do here first is demonstrate the field of view that the thermometer has here. You can see this distance to spot ratio. So if we have the thermometer really close and I take a measurement here, you can see we're reading it's reading actually slightly high. Might have to adjust our emissivity. It's pretty close. It's at 0.95 right now, so that should give us pretty close to the correct value, but we might need to slightly adjust it. But we're off by about a degree. We're pretty close. The laser is pointing right in the center there. Now what I want to show you is when we back this up here, we're going to back this up and I'm going to point the laser, try to hold it on the center there, and you can see our reading here. It isn't that high anymore. It's not at 90. It's because the radiation that's being emitted outside of that black body there is being measured and it's giving us a lower value. So that there demonstrates the importance of the field of view. You can see that where the laser is right now, that exact pinpoint is not where it's measuring the radiation. It's measuring the radiation around the laser pointer, and it's measuring some of the radiation from the cooler objects like the bench and stuff around the calibrator. Alright, so the next thing I want to demonstrate is how reflective surfaces can reflect the radiation. You can see we have a mirror here in front of our IR calibrator, and if I take the thermometer here and I point it, put the laser, you can see it's around the center of the black body. It's measuring 37 degrees C. But if you move the laser down to this table, to the desktop here, it's right around room temperature, about 22 degrees C, and that's what the mirror's actual temperature is at that 22 degrees C. And if I actually even move, so we're not reflecting, so we're reflecting other light off here, you can see how the temperature drops. So just taking note again of that temperature measurement there on the mirror, we're reflecting some of the radiation from the black body over to our IR thermometer. It isn't reading it should be up close to 98 degrees C, but so that indicates that we're not reflecting all the radiation. And when we do some of our experiments in the lab here, we're going to be checking out some other materials, and we might be able to better explain why we might not be getting all that radiation just due to the construction of a mirror. It's got some glass, and it also has a shiny reflective surface behind the glass, so that might help us to explain why we're not seeing all the radiation being reflected towards the IR thermometer. We're not reading the exact temperature of that black body. All right, so right here, this demonstrates the difference between non-contact temperature measurement and contact. You can see we have a type K thermocouple connected to our IR thermometer here, and it's giving that reading, that high reading on the bottom, 97.6. That's the actual temperature of the water in this boiling kettle right here, and I'm measuring on the black surface here of the kettle. You can see it's right around 95, so we have about a 2 degrees C difference here, and that's just the fact that we have heat loss and stuff on the outside of the kettle. I've got the emissivity there, that E value there, set for 0.95 on the bottom, and that's approximately, that should be pretty close to what this surface is for an emissivity, is 0.95. So I'm pretty confident that the outside of this kettle is about 95 degrees C, and that 2 degree difference is very well likely to be the fact that we're getting a surface temperature measurement here instead of a measurement right in the process. So the last thing that I wanted to compare here is how different surfaces here can produce different amounts of radiation. So if we look here, we're measuring about 95 degrees C on the black painted surface here on our kettle, and now if we move this over here to the shinier surface here, the temperature fluctuates a lot, it drops a lot, but it should be the same temperature. We're reading only 66 degrees C, and that has to do with the emissivity value of the surface. If we go over here now to the orange here, we're back up, we're pretty close to, well, we're actually higher, we're right around 97 degrees C. So the different surfaces here have a impact on our temperature measurement. So in the lab, we're going to be figuring out the emissivity of each of these surfaces by using our IR thermometer.